Welcome to this tutorial on sequential counters. A sequential counter is exactly what it sounds like. It follows a certain number count, and it doesn't have to be in any specific order like 0, 1, 2, 3, or 4, and we'll see this in a bit. Everything in a sequential counter is obviously designed sequentially, with one flip-flop passing data to another, and everything is dictated by a certain clock signal. There are two general types of sequential counters. The first is the asynchronous counter, where data is passed in a ripple effect. If we look at the circuit here, we can see that only the first JK flip-flop is affected by the external clock signal, making it an asynchronous counter. If we then look at how the binary counting system works, we can see that the least significant bit constantly switches between 0 and 1. The second least significant bit only changes from 0 to 1 and 1 to 0 when the least significant bit changes from 1 to 0. The third and fourth least significant bits also switch whenever the next most significant bit switches from 1 to 0. Using this pattern, we can make the conclusion that the easiest way to implement an up counter is to use falling edge JK flip-flops. Looking at this up-counting circuit, VDD is always a high value, so that J and K are always inverting the current state. Q0, Q1, Q2, and Q3 are the counter outputs, where Q0 is the least significant bit. After the first falling edge of this clock signal, which is only applied to the first JK flip-flop, the initial state where Q is 0, 0, 0, 0 will be changed so that the least significant bit will be inverted, so that Q is then 0, 0, 0, 1. Since this Q0 is going from 0 to 1, this clock signal input into the second falling edge JK flip-flop does not affect anything, so the rest of the bits remain unchanged. After the second falling edge of the clock signal, however, this Q0 is changed again from 1 to 0, which causes the second JK flip-flop to invert its state, so that the counter's Q output is now 0, 0, 1, 0. Again, since this bit changed from 0 to 1, the following JK flip-flops in the sequential circuit remain unaffected. This pattern repeats to make this 4-bit up counter count from 0 to 31. The second general type of sequential counters is a synchronous counter, where all flip-flops follow one uniform clock signal. Using the same system pattern of changes in the bits of binary upcounting, the first clock signal will cause this Q0 to change from 0 to 1. And since all these falling edge JK flip-flops are following the same clock signal, then none of these flip-flops will be affected by this change in Q0 for the first clock signal. After the second clock signal, this Q0 will change again from 1 to 0, but the 1 output from the previous state will be put into the second JK flip-flop so that J and K here are both 1. This will cause Q1 to be inverted from 0 to 1. This whole pattern follows all throughout as before, but these AND gates are extras to make sure that these inputs J and K are only true when these inputs are all 1. So for in this example, when Q0 and Q1 are 1, then this AND gate outputs a 1 to this J and K, thereby inverting Q2. The same applies for Q3. This works because if we look at this binary counting system again, this third least significant bit, for example, only switches when all the less significant bits are 1. In the next signal, these bits will change back to 0, and this third bit will change to 1. This pattern also applies to other more significant bits, such as the fourth, here. Until now, we've only looked at up counters, but what about down counters? Well, down counters are pretty much the same, except all the outputs of the counter are knotted. So in the up counter, we started with 0, 0, 0, 0, went up to 0, 0, 0, 1, and 0, 0, 1, 0. In the down counter, we start with just the opposite. We start with 1, 1, 1, 1, and go down to 1, 1, 1, 0, and 1, 1, 0, 1. We can see that the first number of the up counter is the exact opposite of the first number of the down counter. We can see the same for the rest of the numbers. They're just the knots of each other. So looking at this circuit, which is an up and a down counter, it's very similar to the up counter in the previous slide. There's just a bit of extra logic and an extra input indicating whether the circuit should be counting up or down. When this input is 1 and tells the circuit to count up, nothing has changed. This extra logic on the bottom has no effect on the circuit. This input into the AND gate is 0, since it's inverted from 1. So all of these AND gates are outputting 0, And these OR gates then are ORing zeros and outputs from the up counter, so up counting has not changed at all. When this input is 0, telling the circuit to count down, then this first clock signal, assuming the initial state is 1, 1, 1, 1, where VDD is always a high value again, then the first Q0 will be inverted from 1 to 0. And since it's a down counter, this input is 0. So 0 ANDed with 0 in this AND gate outputs a 0 into this OR gate, and Q0 is 0. However, this Q0 outputs a 1, and since this input is 0, inverted into a 1, 1 ANDed with 1 is 1. ORed with 0 from here outputs a 1 into this JK flip-flop for the next clock signal. This, of course, inverts this Q1 into 0, and this process repeats, causing the circuit to continuously count down while this input remains 0. Another capability that can be added to counters is the mod function. All we have to do is wire the circuit so that when the output of the counter reaches a certain value, all of the flip-flops get cleared. In this synchronous counter example, these JK flip-flops output A, B, and C, which correspond to the first, second, and third least significant bits in the counter output. The only difference in this circuit from the previous synchronous counter that we should take note of is that certain outputs of the counter are then combined with logic to control the clear functions of the JK flip-flops, resetting the counter output back to 0, 0, 0. In this particular example, when B and C are both 1, then the flip-flops get reset. Since B and C hold binary values of 2 and 4, and 2 plus 4 equals 6, then whenever the circuit counts to 6, it restarts and counts back up from 0. So the useful outputs of the circuit are 0, 1, 2, 3, 4, and 5. The circuit's output is only ever 6 for a brief enough amount of time that this output should be negligible. We may also implement another counter. Its counting pattern is not linear. Note that these flip-flops are D flip-flops, so whatever the input is for a given clock cycle is also the output. Given the initial state of 1, 0, 0, 0, the clock signal will trigger this D flip-flop to input and output a 0 from here, while simultaneously triggering this second flip-flop to input and output a 1. These flip-flops remain 0 for this clock cycle. The counter input then is 0, 1, 0, 0. If we follow the same procedure for the next clock signal, we see that these three flip-flops input and output 0, while this flip-flop input and outputs 1. The counter output now is 0, 0, 1, 0. This process, of course, repeats as usual to comprise what's called a ring counter, where the input bits are shifted left or right. In this example, bits were rotated to the right. As you may or may not have noticed, the sequential counter examples typically counted clock signals. However, clock signals can be converted from mechanical systems. Take this diagram below as an example of a mechanically controlled clock system. There's a stationary LED and a light sensor connected to the clock signal of the counter circuit. The rotary shaft encoder is simply a rotating wheel with holes and walls along the edge to create a pattern of flashing light for the light sensor. This light sensor, when shot at with light, will generate a high voltage signal for the counter, and will generate a low voltage signal when it doesn't sense light from the LED. Therefore, as the rotary shaft encoder rotates, the counter circuit will receive a clock signal that may speed up or slow down with time, depending on what is happening to the encoder. The end result is the counter circuit counting the total number of times that the encoder has blocked off and let through light to the light sensor. If we wanted to make this mechanical system more complex so as to count up when the encoder is rotating one way, and count down when the encoder is rotating the other, we could add another LED paired with another light sensor so that the output of this new light sensor is 90 degrees out of phase with the original light sensor. We choose 90 degrees because then the circuitry may have time to set up and process the data as expected, as there are delays. Note that one LED controls the clock signal inputs, and one LED controls whether the counter should be counting up or down through the D flip-flop. When the encoder rotates in such a way that the signal into the D flip-flop leads the clock signals into the flip-flops, the Q output from the D flip-flop will be set to 1 by every rising edge of the clock signal, so the counter will count up. On the other hand, when the encoder rotates so that the signal into the D flip-flop lags the clock signals into the flip-flops, the Q output will be cleared to 0, and the counter will count down. This concludes this tutorial on sequential counters. Thanks for watching.